In this session, we are going to deal with a material called dielectric. And this material is different from a conductor or a prisma because usually a dielectric material is an insulator. And I want to remind you that when we deal with a conducting material, we have to consider this current in this Ampere's law. But in a piece of dielectric, we don't have to consider this current term because a piece of dielectric cannot conduct electricity. But inside a piece of dielectric, there will be a lot of dipoles. And this is the cartoon for a piece of dipole. And a dipole consists of two charges, one positive and the other is negative, and they are separated over some distance. They cannot move freely, but if you have an electromagnetic wave propagating inside this system, the electric field can induce oscillation of this dipole. And this oscillation process can consume some energy from the electromagnetic wave. So as a result, a wave could also attenuate it inside this material. And from the last few sessions, you already get the concept that if there's energy dissipation inside a material, then the permittivity will consist of imaginary parts. So I write down without any further proof that the permittivity inside a piece of dielectric will also be complex. And this complex number consists of a real part and also imaginary part. And this imaginary part is going to be responsible for the attenuation of the wave inside this dielectric material. So let's write this Helmholtz equation without attenuation and then try to convert it into this expression that we already used for the transmission line because you have to replace this real number by this complex number defined through the dielectric material. And with this definition, you have gamma squared equal to minus omega squared multiplying with mu epsilon. And the solution of this Helmholtz equation is going to be given by this expression if we allow the wave to propagate along plus z direction. And because this epsilon c is a complex number, so this gamma is also a complex number consisting of real part and imaginary part. And the solution in general is going to be given by this expression. So this real part is going to give you attenuation to the wave inside the material. And this imaginary part will tell you how this wave will propagate inside this material. So if I plot this expression on this figure by using the horizontal axis as z direction and this the vertical axis as the amplitude of this wave, then you're going to see the attenuation of the wave over distance. And the envelope is going to follow this exponential minus alpha z term. And this oscillation term comes from this cosine omega t minus beta z. Usually you want to propagate a wave into a low loss system because the energy of an electromagnetic wave is usually quite expensive. So you want to have a small loss in your application. And you also know that the imaginary part of the permittivity is responsible for the loss of the wave inside the material. So let's assume that the imaginary part of the permittivity is small compared with the real part of the permittivity. And in this low loss dielectric, we can calculate the attenuation constant and also the propagation constant. So let's put the epsilon c for the dielectric into this expression. And then because this term is small, so you can expand this term by using Taylor's expansion. And then you end up having the zero order term 1 here, and also the first order term here and second order term. And we only retain the terms up to the second order term and drop all the high order terms because they are too small in our discussion. So with this, then you can put this back to this expression and then identify the real part and imaginary part of gamma. And so you write down this expression. This expression tells you the attenuation of the wave and also propagation of the wave. And alpha is the real part of this expression. So if you multiply this term with this term, J multiplied with the J give you -1. So you end up having this attenuation constant equal to this. And if you want to find out the propagation constant for this wave, then you try to identify the imaginary part of gamma. And we already used this term, so what are left is this zero order term and the second order term. So we copy them down here. Then you can write down the expression for the propagation constant. And so you can see that the attenuation is affected by the imaginary part of the permittivity. And the propagation constant is also affected by the real part and also the imaginary part of the permittivity. And the real signal is given by this. You can multiply the phasor with exponential j omega t and take real part of it to construct this real expression of the electric field. And this term tells you the propagation of the wave. So if you set this phase to be a constant value, then you can calculate the phase velocity of this wave given by this expression. And also you can calculate the ratio of the electric field to the magnetic field. Therefore, you get the intrinsic wave impedance from this calculation. And by definition, the wave's intrinsic impedance is equal to square root of mu over epsilon c. This epsilon c is given by 1 minus the j epsilon double prime over epsilon prime multiplying with this epsilon prime. So if you adopt the Taylor's expansion by assuming this ratio to be small, then you can come up with the expression. It looks a little bit complicated, but the point I want to tell you is that now the ratio is going to be a complex number. This means that there's a phase angle associated with this intrinsic wave impedance. And what it means is that when you try to relate the electric field to the magnetic field, then you have to consider this phase angle in this calculation. This means that in general, electric field and magnetic field are not in phase in a lossy material. And I explained to you when we talk about a piece of good conductor, you send electromagnetic wave to a piece of good conductor, and the electric field will be busy to pull the electrons. And so in general, there's a phase difference between electric field and magnetic field. Well, the same thing happens to this lossy dielectric. The electric field is going to be busy pulling the dipoles, and magnetic field has less interaction with the electric dipole. Therefore, in general, there's a phase difference between the electric field and magnetic field. So in this session, I have introduced you electromagnetic wave in a lossy dielectric. And in general, the permittivity of a lossy dielectric is given by this complex permittivity. And the imaginary part of this complex permittivity is responsible for the attenuation or the absorption of the wave inside the material. And so if you adopt this complex permittivity into this calculation for gamma, you end up having a real part and also imaginary part. And the real part give you the attenuation of the wave, and beta give you the propagation of the wave. And so in general, in the low C material, where you have the absorption to the wave, the electric field and magnetic field are not in phase because the wave impedance is also a complex number. So this is my introduction about the wave propagating inside a dielectric.